All right, so now we're into chapter 5 and sampling, and this is a little different from the analog to digital conversion, which makes a digital value and discretizes on the voltage scale. We also take samples in time, and so sampling is discretizing the measurement but in time, because we sample every few seconds or every so often. So I recommend, if there's one thing you remember from this class, it's the sampling theorem, which we're going to get into today. It's a very simple equation and very powerful when you're setting up sampling. So the big question when you sample a system is how fast do you need to sample? So here is a plot of a signal, a sine wave that's oscillating, and you can see the pluses are samples. They're every so often periodic sampling here. And basically your eye tells you if you have enough points. If it looks like the original signal, then you're sampling fast enough. But we have the sampling theorem to turn that into an equation. So the sampling theorem is here. It's very simple. Fs is the sampling rate, how many samples per second you need to take. And Fm is the highest frequency, not the lowest, the highest frequency in the signal. And Fs has to be greater than 2Fm. If it's equal, it's not quite, just a little bit above is what you really need. So that's the sampling theorem. That's what you should remember. You can totally remember that. As an example, if our signal has a 10 hertz maximum frequency in it, then we have to sample more than 20 hertz. And if you don't sample fast enough, if you violate the sampling theorem, your data will be aliased. And we'll look at pictures of aliasing in just a second. This is a minimum, so Fs has to be greater than 2Fm. But that's just barely working. It's not very good. So 20 times, if you need to put a number on it, is a better rule of thumb for good sampling, and we'll see that in just a second too. Okay, so here is three plots of the same signal. It's a 10 hertz signal. So we know from the previous slide that we have to sample at least 20 hertz, greater than 20 hertz sample rate, according to the sampling theorem. So this is sampled at 5 hertz. This is sampled at 11 hertz. This is sampled at 20.1 hertz. So only the bottom one is following the sampling theorem. And you can see the pluses on here. And those are the sampled values. So if we connect the sampled values with lines, you can see that if we sample at 5 hertz, it doesn't match at all. At 11 hertz, it actually looks really believable. It's a sine wave, but it's a 1 hertz sine wave and not a 10 hertz sine wave. And at 20.1 hertz, this is what we get. If I turn off the original signal, because we don't really know what the original signal is in most cases, you can see at 5 hertz, this is hopelessly aliased. It doesn't look good at all. 11 hertz, hopelessly aliased, and this is the thing with aliasing, it looks reasonable. That, looks like an interesting signal. 20.1 hertz is not aliased. It doesn't look good. It's not a good, smooth representation of the original sine wave, but what it captures is the 10 hertz oscillation. So this signal oscillates at 10 hertz, which is the definition of good enough. So it doesn't catch the high values or the low values, but it's not aliased. So the sampling theorem is very easy to use. About the only trick question is sometimes you're not given Fm and solving for Fs. Sometimes you're given Fs. Our system can sample at 1000 hertz. And then you're trying to find what is the highest frequency that can go in without aliasing. So then you have to divide by 2 over here. So make sure you're solving for the correct F, because they're both in hertz. A critical thinker might notice that this is a very simple equation, but in general, we don't have sine waves. And so what is FM if you're trying to measure, say, the motion of a ship? We don't know what it's not a sine wave, so we don't know what the frequencies are as easily as if it was a sine wave in all the examples. So that is really the tricky part about using the sampling theorem. And we have tools that will analyze the frequency content of a general signal. So we'll be looking at those next. But for now, the sampling theorem is the big one. So remember the sampling theorem, and you'll go far in this class.